Next up, we have Siva and Erik Thorp from Siva Corporation. They're going to be discussing fighting structural corrosion, de-icing chemicals, corrosion, chloride testing, program mitigation.
Good morning, everybody. Just a little bit of clarification of the situation. My name is Erik Thorp with Vector Corrosion Technology. Siva will be coming up in a few minutes. We're going to spend about 45 minutes talking about corrosion. I will be leading off, talking a little bit about some of the mechanics behind corrosion, some of the theory behind it and such, and then talk about galvanic encapsulation. And then Siva will be following up, talking about investigation and chloride, electrochemical chloride extraction. So this is the problem. This is a project that we came across about 17 years ago, and hopefully this doesn't occur on too many of your bridge projects. But this was a project in Chicago, and unfortunately we had to walk away from it. There was too much section loss. And that does happen, but hopefully you don't encounter it that too terribly often. When we talk about corrosion mitigation, there are a variety of options that are out there. You've got discrete anodes, you've got distributed galvanic anodes, arc sprayed zinc, chloride extraction, realkalization, and pressed current systems, and grout impregnation. What I want to do today is talk just about two different ones. One that most of the people in this room are going to be familiar with, which are the discrete anodes, the type 1 anodes, and then galvanic encapsulation. When you look at corrosion, you need to keep in the back of your mind that corrosion is basically, it's a battery. And some of the terminology that we are going to be talking about are really the same sorts of things that you're going to be seeing in a classic dry cell battery. You're going to be talking about cathodes, anodes, electrolytes, and those sorts of things. When you have corrosion, in all instances, no matter if it's due to chlorides or if it's due to carbonation or dissimilar metals, in all instances, the first thing that happens is that you lose that hydroxyl layer that protects the reinforcing steel. When concrete is originally placed, and when you've got a good high pH, you're generally going to have, well, not generally, you're always going to have a nice hydroxyl layer that forms around it. This gives reinforcing steel protection from corrosion. The problem occurs is over a period of time when the environment changes. And for example, if concrete's attacked by chloride, and when that happens, as I mentioned, the first thing that's going to happen is that you're going to be wiping out that hydroxyl layer around the reinforcing steel. The next thing that's going to happen is that you start to form some of these same things that we were talking about before with the typical battery. The top steel becomes an anode, the bottom steel becomes a cathode, and what you'll recognize here is that same battery, those same battery components. The only thing you need is the ionic transfer. And when you have the ionic transfer, which is basically through the concrete, you have the next culprit, the next domino to fall, so to speak, and that's ferric oxide. And when ferric oxide forms, ferric oxide is what we commonly think of as rust, and when ferric oxide forms, the problem here is when it forms, it will expand anywhere from 600 to 800% its original size. And as I think everybody in this room recognizes, concrete doesn't do well under tensile stress. And when you exert these sorts of tensile stresses, that's when you get spalling. This is your typical spall situation, your typical pothole that develops on a bridge, what have you. So what are you going to do? You're going to patch it. It's a natural thing to do. And makes all the sense in the world. Hopefully you're going to put in a good quality patch and you think everything's going to be fine and dandy after that. Well, the problem now is that you've set up a whole new battery system. Now you don't even need that bottom steel. You've got a cathode that forms in the patch itself. That becomes the cathode in the battery, and the anode is immediately next to it. You may have areas that have may only have 350 millivolts of electrical potential, but the problem is they're right next to the patch, and what's typically going to happen is you're going to get corrosion around the perimeter of the patch. This is what's known as ring anode effect or the halo effect. And most of you have probably, most of the people in this room have probably seen it at some point. And it's a significant problem. Here's an example of what that looks like. You can see it around this patch. You can see a second patching that's been done around the edge of the original patch. Here's a bridge. I think this project actually is down in New Mexico, if I'm correct. I think I took this photo down right on the New Mexico border on a small bridge down there, where initially a patch was done. That's the lighter colored concrete, and you can see some other patching that's been done around that. And then this is a project in Connecticut. And unfortunately, this project, I think we counted some 7 different generations of patches. And they did one patch, then another patch, and another patch. And they're basically just chasing their tail on this one. One of the solutions to this is use of galvanic anodes. ACI refers to these as type 1 discrete anodes. And these are comprised of a piece of zinc that is inside an activating mortar. And that piece of zinc is basically forms, this combination forms basically what a mini battery, so to speak. And that piece of zinc, because of its higher electrical potential, will corrode. And you can connect this anode to the reinforcing steel, and it provides a current to the outside, the steel outside that patch, out in this area, out here, basically protecting this. And again, the majority of the DOTs here are using these actively, and it's proven technology that has worked very, very well for the last 15 years. Here is an example of some of these going in. This is a smaller project. You can see the workmen placing these anodes around the perimeter of this repair patch. Here's another example of this. And then here's a pile cap on a marine structure. And you can, if you look carefully here, you'll see the anodes right up there. So far, we've been talking about point anodes. And those point anodes, as I mentioned, provide that current around the perimeter of the patch. There's another system that's out there, which is a distributed anode system. And distributed anodes are basically larger linear type anodes. Typically, they've got more zinc in them. And now what you're able to do with these distributed anodes, these larger anodes, is you're able to protect a much larger area. You can get much greater service life out of it too. And you can also deal in a much harsher environment overall too. This is what it looks like. Basically what you have in this particular system is a tubular anode, and here you can see it going in. These come in a version that can be anywhere from 6 inches in length to as much as 6.5 feet in length. It has a solid core of zinc surrounded by that activating mortar with a zinc foil, and then a mesh on the outside for handling purposes. In this particular case, this is being installed at the interface between a chloride-contaminated area and some new concrete that's going in. It will be protecting the steel in this area with new concrete. Here it is in an expansion joint. You can see on the left-hand side, if you look carefully, you'll see a slightly green area there. That's the distributed anode that's been placed there. And then here is a barrier wall system. This is for Iowa DOT. They had some barrier walls where they're having some issues, some significant corrosion at the base of those barrier walls. And here's a marine application. This is a slightly different version. Instead of that tubular version, this is one that looks, it's kind of like a 2x4. This has, it's a slightly different technology, but it's got the capability of providing current either wet or dry in a saltwater environment. And this has 2 pounds of zinc per lineal foot. It's a lot of zinc overall. And then here again, if you look at this, this is that same system being placed in a pile cap right there. With this technology, it opens up some other possibilities that you wouldn't have otherwise. And you may, thinking that original slide that we looked at, 17 years ago, we had to walk away from that project. There's so much section loss that the only solution was replacement at the time. But over the last 15 years or so, we've been doing a lot of marine installation, a lot of installations of galvanic anodes in the tidal zone area, in the tidal zones for piles. These are some of the most aggressive environments when you look at corrosion overall. You've got salt, obviously from salt water, huge presence there. You've got oxygen and moisture, and it's being activated with the tide going up and down. And what you'll see is you can find some pretty significant corrosion in these areas. Areas like this. This is actually down at Port Canaveral, I believe. And for the last 15 years, we've been using these distributed anodes typically in a pile encapsulation or a pile jacket type system. And here what you'll see, what we do is we tie the anodes to the reinforcing steel, and then we encapsulate the anodes inside concrete or grout. And what you'll see here is there's typically a jacket on the outside, but these are encapsulated within that grout or the concrete. And now what you're able to do is provide that same current that we were looking at with the, it's basically the same concept as those little point anodes or those puck anodes, but it's just done on a greater scale. But you can work in a very, very difficult environment and still get some terrific protection over a long period of time. Here's what these same anodes, these 2x4 type anodes, the marine version of the distributed anode look like. They've put together a series of these. And you can use, we've been doing this for quite a while, and you may only use one anode, one distributed anode on a pile. You can use as many as 8 in this particular case. They're tying them on and attaching these to the underlying reinforcing steel. Here it is. This is actually up in above the tidal area. That's one of the advantages of this particular system, is it can work in either wet areas or in dry areas. They've got a continuity ring that they've opened up all the way around this particular pile, so that they're making sure that all of the steel is continuous, electrically continuous, and they're attaching a series of these. In this case, they're putting a jacket over the top, and this is a PVC jacket. For quite a while, for a long time, we've been using fiberglass jackets for this. We're actually now starting to go to a PVC jacket. There's a spacer system on it, and if you look here too, you'll see that these are the anodes there that are wired together and attached. This is where they are right here, wired together, attached to the underlying reinforcing steel. This is prior to a grout system being placed to encapsulate the whole system. This is what it looks like after the fact. And this is a project out in, for California in San Leandro. It was done a number of years ago. And you'll notice that there's some junction boxes at the top of this that are used for monitoring the performance of the system. Now, one of the nice things about this approach is that you can also go in and add reinforcing. This is a project where they've added some reinforcing to it. You're not limited by staying with the original reinforcement. And you don't necessarily have to use a jacket on this either. In this particular case, this is just a form and place system that's not using a jacket. So we've been looking at a very, very difficult environment and marine situation. This is a bridge in Minneapolis. And this is a project we came across a couple years ago. They were looking at replacement on this. And they thought that replacement was probably the only way to go. This is actually an easy installation compared to what we were looking at for those same tidal jackets that we're doing in a marine area. But we're facing the very same problems. It's really no different in that regards. And this is what we ended up doing on this. You'll see on some of the piers in the center there, they're still being exposed, but you can see that we've gone in with an overbuild on this, putting in those galvanic anodes to protect those piers. And this is another area on that very same project in which we've done an overbuild with the galvanic anodes, the distributed anodes underneath. This same thing can occur in other areas on bridges too. We've done over 35, I believe, repairs for Ohio DOT on some of their slab bridges. And on slab bridges, what you can be facing is, one of the more difficult areas everybody here realizes on any bridge is certainly the expansion joints. And on these bridges, they're having problems on the expansion joints. Salt-laden water was going down to the abutments below, causing spalling. And while that doesn't look too bad on this particular schematic, this is what it looked like once we went in and we started doing some chipping on it. There's some pretty significant spalls on this. This was a project that we did some 10 years ago. It was one of the first projects we did for Ohio DOT. One of the nice things about these abutments is they've got some large footers on them, and because of the larger footers, we were able to do some overbuilds. And with this overbuild, we put in new reinforcing steel and attached the anodes to the underlying steel. And this is what if you look carefully here, you'll see the green areas. The green component here are those distributed anodes tied to their underlying reinforcing steel. And we formed it, placed the concrete, and this is what it looked like after the fact. And if you look up in the upper right here, you will see, up in here, you'll see a junction box, also up here. We monitored this first one we did for Ohio DOT, we've monitored this for the past 10 years. Actually, it's now up to 11 years. And we initially were projecting service life of some, I think it was 15 to 20 years. We're now looking at this at 35 plus years of service life. One of the advantages of this system is that you also get a higher level of protection. With those discrete anodes, the little puck-type anodes, the level of protection is down in that pink curve. With the distributed anodes, it provides more current, and we're up in the cathodic protection range. Some other applications. Here are some pier caps where they've been installed. We can do decks. This is, again, in Ohio. This is Lake County in Ohio. There are 3 bridges. They are looking at replacement on this. We went in with hydro demolition, and they removed it down to the top layer of steel, installed a series of these distributed anodes here, came in with some low slump concrete, and were able to basically save the bridges. Camp Pendleton, California, similar situation. I worked on this project myself, and this is a bridge that's about 300 feet from the Pacific. It gets a lot of salt into the area, and on this one they did basically the same thing, coming in with a new layer of steel with the distributed anodes. Port of Portland, this is a potash loading facility for the Port of Portland, in which we installed some of the distributed anodes. And then finally, this is a project up in Ottawa. We're now doing this more and more on bridge replacement projects, quite often on the substructures on those bridge replacement projects. This was a project that was done a few years ago, had some pretty serious issues with it, not just on the abutments, but also on the superstructure and the deck. They ended up deciding that they had to remove the superstructure and deck, but we were able to save the underlying abutments. We were able to do the work in advance by installing these distributed anodes. We went in, as you can see, you have to look carefully here, but there's a series of distributed anodes placed on these abutment these abutment walls. They came in over a 2-day weekend, and they removed the existing deck. They had been just off-site, just slightly off-site here. They had been pouring and putting together a new bridge. They came in with their lift system here. They took out the old bridge one night, dropped that new bridge in, replaced it, and over that 2-day weekend, they were able to do this entire project. So with this in mind, I guess the main takeaway that I'd like to suggest is that you now have some alternatives. You may be looking at projects that it may be the entire project you're looking at replacement, but when you have highly corroded reinforcing, and you may be looking at replacement, and certainly that is the right way to go in a lot of instances. You may be looking at replacement for the entire bridge or maybe components of it. The other option that you have is that you can go in and either with the entire project or with different parts of the project, you may want to consider galvanic encapsulation as another tool in your toolbox, so to speak. So with that in mind, I will say that it's okay for corrosion to visit, but you hopefully don't want to let it bite. I'll open up maybe just for 2 or 3 minutes of questions, and then we'll bounce on over to Siva. Anybody have any questions?
What are the lifespans of the anodes?
It depends the size of the anodes. We can use as little as a 0.2 pound of zinc anode up to a 2 pound of zinc anode, and the spacing. And we've designed projects. Typically, we start with 15 to 20 years of service life. That's the starting point. But I've designed projects for as much as 75 years of service life. And as you can see from that ODOT project, that was one that we originally designed for 15 to 20 years. We thought that's all we were going to get out of it. We're finding we're getting even more than we originally thought on a lot of projects.
Could you go into a little more detail as to that chemical reaction that occurs when the contaminant goes into the concrete to destroy the hydroxyl layer, like the exact chemistry that's going on there? Because I think a lot of people miss that, and some of the repair procedures that could be done, to mitigate that or to keep that from happening, kind of get washed away.
Wow, I'm not sure I'm necessarily the right person to do that. I might even turn that one. Siva, you might even want to go into that when you when you talk.
Valuable to the group, Siva, because I run into a lot of situations where people don't do the proper steps in relation to preserving their structure. They'll go into a massive repair, but forget to mitigate that initial chemical reaction, so that they do in a proper sequence. So understanding that chemical reaction, I think, would be very important for the group, so that they really understand what's going on there.
We could probably get somebody more qualified than I, as you know, Dave and some of the other people with a Vector that can probably speak to that for the next hour or so, and in regards to some of the chemical reactions going on in that area. Yes, we can use sealers and other things to block the chlorides from getting in there. It's a complex chain of things that takes place in that regards. And it's something that is clearly, if you can keep the oxygen out, if you can keep the moisture out, the contaminant out, you're certainly going to go a long way in protecting against corrosion. The other side of it is that if you can build up that hydroxyl layer, you can do a very good job of protecting against corrosion in the long run too. And that's one of the things that you get out of galvanic anodes, is that during the entire time that they are there, they are providing a current, and while that current is being generated, the hydroxyl layer is increasing the entire time.
So the hydroxyl layer can be developed with the cathodic protection.
Yes.
Now, what about deacidifying the concrete?
I'm not qualified to speak to that. I'm not the right person in that regards.
Can you talk about the use of anodes in deck patching where the adjacent concrete has chlorides but is well below the critical limit there? Is that still beneficial or a waste of? Yes,
because what happens when you place that new patching material there, you may have had corrosion, but it may not have spalled yet. But what happens when you place that new concrete there, you increase the amount of, you increase the corrosion rate. You're basically kicking it into gear that much higher. As you may notice, generally, when I show most of my slides, I'm going to show 500 millivolts as the area that you may have active spalling taking place. And you've noticed in that slide, I only showed 350 millivolts. You may get, it may kick it into gear that you have an area that only had 300, 350 millivolts, but all of a sudden now it kicks it up to a whole other level that you didn't have before because of that ring anode effect. Now, again, because of the proximity of that whole situation, you've got your patch, and immediately next to that patch is you've got chloride-contaminated concrete. And right at that edge is you're going to get that grade increase as far as corrosion.
Thank you, folks. I appreciate the opportunity to talk to you all. And I know we had a lot of questions here. I can talk about that. Whenever the corrosion occurs, typically what happens is that iron becomes iron oxide. And then the iron oxide reacts with the chlorides, becomes ferric chloride. And when that ferric chloride comes, it moves away from the steel, and then the chloride is removed, and then it goes back to doing the whole process again and again. So that way, when you have enough chlorides, the corrosion can continue on forever. You have more chlorides, the rate increases. That's the reason why, when you ask the question, if you have an adjacent area that doesn't have enough chlorides, right? It's only at the surface, not at the rebar level. Will that work, right? Because the steel is still passive next to it. Only in that area where the chlorides have reached, you have that damage, right? In that case, you're really not going to get a whole lot of, you could just simply patch it, it'd be fine, because now your patch potential is passive, right around it is passive, as long as you know it is passive. So there's no difference, so you're not going to be affected. What you're doing when you're doing the patch, when you have a corroding steel there, and you make that passive, right next to it there's a corroding steel, when you put the anode, you make that patch area also active. So the difference is very minimal. That's how you stop the corrosion. Is that clear? Yeah. Good. So having said that, let's move on. We always talk about, structures that we build. And for the first 40 years, the structure is in pretty good shape, really no problem. And it's had some cracks, it says some chloride's going in there. And you got the first visible damage. We don't run out and fix and do a major, investigation. We just do the patch and move on. But the patch actually typically accelerates corrosion. The reason when you have spalling is because the chlorides are going everywhere. And we'll talk about it. When you have a deck structure or substructure or whatever, your cover varies a lot. Even though your design cover is 2.5 inches, you don't have 2.5 inches everywhere. It could vary from 2 to 3 inches. Sometimes it's 1.5 to 3.5. I don't know. So the corrosion starts where you have low cover, and that's where you have that issue, right? And then it keeps increasing over time. But if you don't do anything, it keeps accelerating, right? From 40 to 60 years, for the first 40 years it was fine. The next 20 years, we ended up going from okay to having to do a major rehab or replacement, right? If you don't do that, you would end up with a potential emergency situation or a failure where you spend a lot of money addressing the issue. So what do we do, right? Well, we want to address this issue before it becomes a major problem, particularly in the pre-stress post-tension structures. When you're talking about it, you really want to take care of that in the first sign of problems. Otherwise, as you know, in the new Oregon bridge, right? The Althea Bridge, is that right? They had put in the post-tensioning pre-stress pier cap, post-tension pier cap, and those strands were corroding in 6 to 8 years? So it can quickly go, and I've seen structures fail in about 7 years from construction to the first failure of the strand. So it can happen pretty quickly, but regular reinforced concrete structure is a little bit more forgiving, right? It fails and you can see it, I'm corroding, I'm hurting, come and pay attention to me and that kind of thing. But even that, if you go beyond a certain point, you're going to spend a lot of money fixing it. So the question is, when do we interfere in these structures? In the past, we would interfere right before the red line, right? Who get to spend a whole lot of money or replace them. But nowadays, what we really want to do is to get ahead of the curve, to try to do it early on in the process where your options are number of them and your cost is much lower to handle those situations. So kind of giving a primer on this, here's an example of a structure where I-95 was completely closed because of the huge crack on the column. And the crack may not necessarily due to corrosion, but corrosion leads to that if you wait long enough. And so if you want a 100-year life, right? In the past, we talked about, Alsea Bridge is probably about a 50-year life design. And, all the structure that we have built up until 70s and 80s, even 90s, we had a service life of 50 years. At the end of 50 years, are we going to replace them? Probably not. It's expensive to replace them. So what are we going to do? We got to extend the service life. How do we do that? What system do we use? How do we get to that? But prior to that, these are the properties that you need, with regard to the strength, with regard to resistance to freeze thaw, ASR, resistance to chloride penetration. These are all the things that you need to make sure your structure is going to last 100 years. Now, I'm not going to focus on every single one of these today. I'm going to focus primarily on your chlorides and how it gets into the structure, how fast it goes, what controls that penetration rate, so to speak. The diffusion coefficient, I'm jumping about 10 steps because I have only 15 minutes. What it is second law of diffusion defines how fast the chloride goes in through the concrete. Concrete is like a hard sponge, You look at it as a hard sponge with holes in them. Some of it, we actually design holes in them and distribute the holes so that you have freeze thaw resistance, right? But generally, even if you don't design, concrete has holes in it, and the water goes through it, salt goes through it. And so the question is, how do we figure out how fast it goes, right? It's the property of the concrete. And that's what we want to measure with the diffusion coefficient. We are measuring what is the property of the concrete. So you take an existing structure, you take a number of cores, you slice those cores, you know the data and surface chloride, you know the chloride at the rebar level, you know the cover. Using that information, you get those diffusion coefficient. Use that to predict how long would it take for those chlorides to get to the steel level. Now you have a property that helps you to predict your future deterioration, right? And that's what we're trying to do here. Here is an example that I'm talking about. Typically, our structures have a diffusion coefficient somewhere in the 0.03 range, which is the green line that you're talking about there. Now, what I'm showing here is your cover could be 1.5, 2.5, 3.5 inch cover, right? The 2.5 inch is typically deck cover. 3.5 inches your substructure cover, and some, in Florida, they've got 6 inch cover. I'm not going to talk about that. This is our typical 2.5, and 3, right? When you look at this, if you have a structure with a very poor concrete, right, it doesn't really matter what cover you have. That life is pretty much fixed. It's 10 to 30 years, that's it. You're going to have to address this problem, right? However, if you have concrete like we normally use today, you're looking at, the life is about 20 to 60, 70 years. And that's what you see, 20 to 70 years, right? At some point in time, you have to interfere. For example, if your cover is 1.5 inches, there is no difference between your really poor concrete and the concrete that we use. So the cover really is your first line of defense. And second is the concrete quality. And then you go on to your, resistant reinforcement, corrosion resistant reinforcement, things like that, right? And we got some new ones that one of the folks, AZZ, is doing. It's a new form of zinc, I guess, right? Zinc-coated rebars. When you get to the very good concrete, right? Now, the life of that is primarily defined by what is your cover. If you have a low cover, you're going to have low life, right? So you really are dealing with cover and the quality of the concrete to define your life, 100-year life. Having said that, when you have chlorides, right, we talked about this. When you have 1.2 pounds of chloride, corrosion initiates. Now, there are a lot of people using a lot of different numbers. Somebody uses 2 pounds of chloride. Some people swear by 4 pounds of chloride. but the research by Federal Highway and other folks, indicate that about 1.2 pound the corrosion initiates. Now, that doesn't mean you will have a concrete damage at 1.2. It depends on all the other factors, right, before it shows up. But that's where the corrosion initiates. This is if you have a new concrete or with a high pH, right? If you put a piece of steel in water and soil, when does it start corroding? From day one. When you put the same piece of steel in concrete, because the concrete is high in pH, it forms a film that protects it from chlorides and water and air and all that. So you have to break through that film, and that requires certain things, right? So that's what you're really looking at. If you have, for example, in post-tension structures and grout issues we're talking about, if you have a grout that's of poor quality, that strand is corroding from day one. You don't need any chlorides, period. And that's why you really need to look at the quality of the grout and not just the void, not whether there's water or not. So really, that's critical. You want to know how much chloride is there. You want to know what's your pH. You want to know a number of other things, right? Before you can decide what is my life. What's the structure that I'm dealing with? What's the life that it's going to have? Next thing is, you not only not want to know just the chlorides, but you want to know where these bad areas are within your structure. For example, in a pre-stressed beam, if you have corrosion on the beam ends, right, and the strands are corroding, everywhere else it's fine, so typically you have a 5% damage. However, if you don't address that, that structure may lead to serious corrosion problems, which then end up in replacing not only the superstructure, but you have to replace the deck as well. So it's really important to know where those critical areas are, and if those areas are corroding, you need to address that immediately, right? Otherwise, in general, if it's a compression member, concrete is good in compression, right? You can sit and wait a little longer to address those things. So you really want to know and develop a evaluation program to make sure that your diagnosis is correct, and so that your solution or the treatment that you're going to prescribe to that patient is going to be effective, and the money you're spending is going to bear the fruit that you want. And if you do it right, you could save significant amount of money and extend the service life of the structure. You could touch 4 to 5 bridges instead of replacing just one, right? We're talking about a number of different tools you need to properly diagnose the structure. What's the condition? Where is it going in the future? A lot of the times we decide based on where the structure is today. And we wait until we're able to see that the patient is really struggling before we enter in. What we want to do in the preservation or proactive mode, we really want to know where is this patient going to be 10, 25 years from now? If he's moving in that trajectory, if he's going to get there, he's going to have problems, right? We want to address it today. For example, folks are having some issues or health issues, right? If you let it go, it's going to have problems. And you address it today, then they live longer. The same concept here. So I'm not going to talk about a lot of the NDT and different things. Everybody knows about it, so I'm going to keep skipping on. With regard to the laboratory, to determine what the property of the concrete that resists chloride penetration. There are a lot of different tests. But one thing I really want to talk about is if you take proper sampling and the number of sampling throughout the deck, it's distributed, then you have a much better input data to predict where the patient is going to be 10 or 25 years from now. If you take very minimal data, you may predict the patient's going to be okay, or you may predict the patient's going to die. Either one may be wrong, right? So if you have sufficient number of data and distribute it throughout, then you have a much better picture of where he's going to be. So if you look at this is a 4-inch core, right? You look at that 1-inch circle, which is the center, black circle. If you take a 1-inch powder sample, a lot of folks, including me, have taken in the past. When you take that and you use a 3/4-inch aggregate in a concrete and you drill at the 1-inch core, drill, you may end up getting all of the aggregate, very minimal of the paste. What happens when the chloride goes through? Does it go through the aggregate or through the paste? It goes through the paste, correct. And so if you're taking aggregate sample, your chloride variation is going to be serious, right? It's going to be very high, very low, it's all over the place. If you increase the number of sampling, the variation is not going to go down, right? Still going to keep going up. It's a flip of the coin, right? So whereas if you increase the size to 2 or 3 or 4 inches, right? Now you're getting a real representation of what's going on in the structure. So you slice the entire disc, you powder the whole thing, and you take the sample and digest it and test it. Now you got a better handle on what your chloride is. And you're doing the profile will be better as well in terms of being able to curve fit that profile. Using that in the service life analysis is going to be really good in terms of being able to better predict what the future is going to be for this. This is the typical procedure. I'm going to skip that through, which we talked about. Here's the case study of one of the bridges that we worked on. It's a 5-span bridge, and it was built in 68, so 50 years, 45 to 50 years. This is the condition of the structure, right? It's got problems. We know that it's got problems. And we've collected data. Here's a summary of the data. You can see there's significant damage that's already occurring on the structure, except the abutment is starting to occur. And your average cover, you see 2 to 2.7. Now, when you say the average cover, that's the average cover, right? The defined cover is about 2 to 3 inches, depending on what they defined in the design. But the 95% cover tells you, based on the statistics, at least 95% of the structure has this much minimum cover. You look at those numbers, 1 to 1.5. So even though you have a 2.5, 3, you can go as low as 1 to 1.5, right? So that's one thing. So this variation in cover is what I'm trying to get at. Now, if you look at the chlorides, 1,000 parts, that's 4 pounds of chloride. You got 4 pounds of chloride at the rebar level, 60% of the cap. 17%, 25%, right? So you obviously know there is significant amount of chloride in there, right? You have damage, you have chlorides. Now you got the diffusion, right? Average diffusion coefficients, 0.07, 0.02, and 0.04. We talked about 0.03, the green line, right? It's 0.03 to 0.07. When you have a 0.07, it's a bad concrete, we know, right? It's not having a great property. So you would expect a higher damage, right, in a shorter period of time. And so if you look at this, using this information, you do a service life analysis, project your future deterioration. As you can see in the cap, it's already 25%. If you don't do anything, it's going to double, right, in about 20 years. And at that point, your option is very limited, right? You're going to be expensive, any repair you do, or you're going to have to replace it. Same thing with the pier columns as well. Deterioration is high, and it's going to keep going up, right? So the time to intervene to change the trajectory of these deterioration is today and not wait any longer. Whereas when it comes to abutment, as you can see here, it's 4.2. It's starting to deteriorate. It's got significant chloride. It is going to deteriorate. However, the damage, projected damage, is going to be far into the future. So you could wait another 10 years and see where it develops, and then make a decision what you want to do. In the meantime, you can use those point anodes that Erik talked about at those areas where there's damage and work with those, right? And so we looked at different options for the piers as well as the abutments, impressed current or ECE or global anode, right? Galvanic anode systems. And for the abutments, we primarily looked at ECE or discrete anode. One other thing is that when we are looking at rehab, we don't look at, we'll do it, this particular system for this cap, and column will do something else, and, abutment will do something else, and another bridge will totally do something else. It's not really effective, cost effective for the owner, right? You want to synthesize all that, and I'll talk about next, case study. So we try to figure out what is 1 or 2 things we can do to minimize the cost. And we talked about the contractor yesterday talked about, hey, group those projects together, keep it one type of, system, so you get the better cost, right? And you look at this on a pier cap, we did the not only the initial cost, we also calculated through the life, what are all the things we have to do, what's going to be the life cycle cost for 25 or 50 years. And based on the life cycle cost, and this is at the present value, right? Then you can compare and rank them, all these different options you rank. Then work with the client to figure out which option is best for them, based on the schedule and the cost they have and things like that, right? So that's our recommendation for this structure. And here's one thing, when you talk about ECE, there are some limitations, right? You can't use every solution on every project, right? You take one hammer and hit them all with the hammer, right? With the ECE, you're using a lot of current. So if you have a high-strength steel, you're going to end up with hydrogen embrittlement if you use this, so you be careful. You also generate a lot of hydroxyl ion at the steel interface. So if you're using this, be careful. If you have ASR issue, ASR gets aggravated in those situations. Now, if you also have a lot of chlorides behind your steel, you may not be able to pull it out because the field works only between your surface anode and the first layer of steel. A lot of the currents go in there. So your effect is only between those 2 points. So you try to use this, with those limitations in mind, because you got a lot of different options, right? So here's another project we worked, ECE and sprayed anode, 11 different bridges in a 10-mile corridor. So you're looking at this, you really want to know, hey, what are the 2 things or 1 or 2 things I can do to extend the service life of all these 10 or 11 bridges? And that brings some efficiency and cost to this process. And that's what we did on this. And that's what it looks like, some of the ECE. I just want to put a couple of slides in there. What does it look like? You established an anode on the surface, you establish electrolyte, and you cover that all, and you pass current through it, and you can actually measure the current output right here. And based on the total amount of current you put, like total over time, you know that you're removing chlorides. And then you can also test for chlorides at different places where you know the chlorides are high and measure them coming down. And then the end point would be when the chlorides are below a certain point, you terminate the ECE and you're done. And so having said that, I really want to thank you for your time.